The computer uses memory to store data and instructions. These data and instructions are held in the memory and accessed by the CPU when it wants to retrieve an instruction or a data item associated with that. The best way to look at memory is to compare that with the locker cabinet that you find in various places. The locker cabinet has large number of lockers. Each locker has a specific size, which allows us to keep one item of a specific size in the locker. Also, each locker has a number associated with that, like an address. So this number helps us to uniquely identify a particular locker from the locker cabinet or the locker room where all the cabinets are located. Now inside a computer, the memory is also a long array of what we call memory cells. Each memory cell is capable of storing one binary word. So a binary word can be either 8 bits, 16 bits or 32 bits long depending on the data bus size of the computer. Now each memory cell also has a unique address associated with that. This address helps the CPU to identify each memory cell uniquely in the large array of cells available in the memory. The address itself is again a binary bit pattern. So each memory cell has a unique bit pattern associated with that. We often represent this bit pattern as a binary or hexadecimal number for our convenience. There are no two memory cells in the memory which has the same address or the same bit pattern associated with that. Then let's look at how the CPU communicates with the memory. Now when communicating with the memory, CPU needs to tell which exact memory cell that it wants to access for either reading from data or write data into that cell. For that, it uses the address. Now this address is sent through the separate set of communication lines in the system bus, what we call as the address bus. So the address bus is controlled by the CPU, which means the CPU always sends the address to the memory, telling the memory which memory cell that it wants to access. Like in the locker room, we telling which number of the locker that we want to open. Then also the CPU need to tell the memory whether it's going to read data or write data into the memory. For that it uses a separate set of lines called the control bus. That's also part of the system bus. The control bus tells the memory whether it's going to write data into the memory or read data from the memory. Then finally, we have another mechanism to transport data between CPU and memory. Once we specify the address and then we tell the memory whether to store it or read it, then we also need to either send or receive the data from memory. For that we use the data bus. The data bus is a bidirectional bus, which means that the same set of lines can be used to send data to the memory as well as in the other direction to receive data from the memory. Whereas if you look at the address bus and the control bus, they are unidirectional buses, which means their values originate from the CPU and they goes to the memory. The CPU is the one which tells the memory through the bus which cell it want to access and whether it want to write or read the data. So as a result, sometimes we call the CPU to be the bus master, which means it controls the bus. It decides to where it want to write data or from where it want to read data from. Then also the size of the address bus determines how many different memory cells, how many different addresses it can communicate. So in that context, it determines the size of the memory that the computer can be provided with. So because each memory cell has to have a unique address and that address has to be communicated through the address bus. So the size of the address bus or the capacity of the address bus determines how many different memory cells that we can accommodate in the memory. The size of the data bus determines what is the size of a single transaction. How many bits we can send through a single transaction. Transaction means either writing to the memory or reading from the memory. If the data bus is 8-bit wide, that means we can send 1 byte, either write 1 byte or read 1 byte from the memory at any given time. If it is 16 bits, that is equal to 2 bytes, right? So that means the CPU can either write 2 bytes at the same time to the memory or read 2 bytes at the same time memory. In our locker box comparison, you can imagine the size of the locker to be the width of the data bus. If the locker is large, then we can put a large item in that. Similarly, if the data bus has more bits, that we can send more data, a large range of values in a single transaction. If the locker is small, only we can put a small amount of things in the locker at any given time. So in that context, if the data bus width is small, we can only send a small amount of data at any given time. If the locker cabinet has larger number of lockers, then we can put many different items in the locker at any given time. Similarly, if the data address bus has a larger width, larger range, then the computer can have more memory associated with that. The interactions that the CPU will have with memory during the operation is often called memory transactions or memory cycles. It's called a cycle because it's the same action that happens again and again for every read operation or every write operation with the memory. There are two types of memory cycles. One to read from the memory and the other to write into the memory. Both these cycles have a carefully sequence of activities that need to be carried out by the CPU to get the operation done correctly. So let's look at the memory read cycle first. We know that the CPU is the bus master, which means the CPU is the one which decides from which memory location that it is going to read the data. So the first thing that the CPU need to do here is to tell the memory which location that it want to access for the read operation. And that is done by sending the address of that particular memory cell through the address bus. When the memory receives this signal, it knows that the CPU is planning to either read or write from this particular memory location. Thereafter, the CPU need to tell the memory that it is going to read from that location. And for that, the CPU will activate the memory read signal. That signal indicates to the memory that, okay, CPU is waiting for data which is stored in that particular cell. So the third step is that the memory will copy that data in the cell into the data bus. It's important to remember that when you read from memory, we always get a copy of the data, which also means that the original data element in that particular cell within the memory does not get erased or changed by a read operation. So once the memory has put this data into the data bus, the CPU will sense that and CPU will read that data item from the data bus. And thereafter, the CPU will use that accordingly in its internal operation. So memory read cycle has 4 steps. First, the CPU set the address on the address bus. Then CPU activate the read signal, memory read signal to the memory. Then the memory will copy the content of that data element or a memory cell into the data bus, and the CPU will pick the value from the data bus. And for that purpose, since the data is going from memory to the CPU should configure the data bus to receive data and for the memory to send that data. Next, look at the memory write cycle. Like in the read cycle, memory write cycle also needs the CPU to tell the memory to which memory location that it is going to write with, or which memory location that the data should be stored within the memory. That is again done by sending the address of that memory cell through the address bus. So when the address is received, the memory knows that CPU is going to access this particular memory location for the next operation. Thereafter, the CPU need to put data into the data bus. Now the CPU is sending data. So it has to put the data into the data bus, and for that purpose, the CPU will configure the data bus so that it is in the output mode, so that it can send data from CPU to the memory. After putting data into the data bus, the CPU will tell the memory, write that into the corresponding cell. Because now we have the address in the address bus, we have the data in the data bus, and the control bus signal will tell the memory that the data has to be copied into the new memory, the addressed memory cell. And for that purpose, CPU activates the memory write signal in the control bus. When the memory sees these signals, it knows that there's a valid address in the address bus. there's a valid data in the data bus and it has to copy the data bus content into the memory cell. And when you do that copying, it will overwrite any previous value that was held in that memory cell. So that completes the memory write cycle. So these two cycles are the most often cycles of the system. Each time the CPU reads a data item or even an instruction, it executes a read cycle, memory read cycle. Each time it wants to store something on memory, it executes the memory write cycle. Now, since each of these cycles are having multiple activities, they also occupy some time in the execution process. Each of these signals has to be sent one after the other. So memory read and memory write are time consuming activities in a computer. Hence, they also contribute to the speed at which the computer can run. If you have a faster CPU and a faster memory, which means that the CPU can interact with the memory with very efficiently, and the memory will be able to carry out the frequent read and write operation within a very short period of time. If you design a system with a faster CPU and a slower memory, still you will not be able to get the best performance out of the CPU, because each time when the CPU wants to write or read from the memory, there will be delay because of the slowness of the memory. The other way around also it will not work. If you have a faster memory and a slow CPU, even though the memory is capable of working fast, there will be a delay in sending data and receiving data by the CPU. So to get the optimum performance, you have to make sure that the speed of the work of the memory and the speed of the transaction that happens from the CPU match perfectly with each other.